On September 1st of last year, a group of 16 researchers made a notable disclosure that sent shock waves through mainstream researchers. They distributed a paper specifying their discoveries, which tested our key understanding of the universe utilizing the James Webb Space Telescope. These scientists noticed far-off universes and uncovered something genuinely unforeseen. Until this revelation, the overall thought in astronomy was that the universe went through a time of quick expansion followed by a cooling stage. This cooling stage ultimately prompted the formation of the first stars and galaxies during what researchers allude to as the Dark Ages. Anyway, the systems seen by the group appeared astonishingly developed, looking like our own Milky Way and showing a degree of development far beyond what was guessed. This disclosure proposed that these ancient systems probably existed well before our own. This finding conveys significant implications for how we might interpret cosmic history. It challenges the conventional story of the universe's origins, especially the broadly accepted idea of the Big Bang as the conclusive starting point. Prior to the mid-19th century, the common view among researchers was that the universe was static and eternal, with no expansion or contraction occurring. This belief was overturned by the observations of astronomer Vesto Melvin Slipher, who noted certain clouds displaying rapid movement away from us, attributed to the expansion of our own universe. Further observations, especially from the Lick Observatory in Arizona, contradicted this explanation. The crucial figure in unraveling this mystery was Edwin Hubble, who showed a clear relationship. The farther a galaxy was from us, the faster it appeared to be moving away. This observational evidence aligned with the predictions of Albert Einstein's theory of general relativity, which proposed that spacetime could expand or contract. By tracing the universe's development backward through time using the equations of general relativity, researchers arrived at the concept of a singularity, a point of infinite density and temperature from which all matter and energy began. This singularity is often associated with the event known as the Big Bang. However, this raises significant questions about what existed before the Big Bang. Was there really nothing, no space, no time? Or are there aspects of cosmic history that remain beyond our current understanding? To conceptualize this idea, consider the analogy of the surface of a balloon. Imagine our universe as the surface of the balloon expanding from a smaller size to its current dimensions. As the balloon expands, objects marked on its surface move farther apart, illustrating the concept of cosmic expansion. In this framework, the scale factor serves as a measure of the universe's size, similar to a ruler used to measure the balloon's dimensions. At present, our universe has a certain scale factor, but in the past, it was smaller. As the universe expands, galaxies and other astronomical structures move away from each other, driven by the stretching of spacetime itself. In the future, the scale factor of the universe will continue to increase, reflecting the ongoing expansion of the universe. This perspective offers insight into the vastness and complexity of cosmic history, inviting further exploration into the mysteries of the universe's origins. As you slowly let the air out of the balloon, everything on its surface begins to move closer together. Eventually, if you were to completely deflate the balloon, you'd be left with a small, flat piece of rubber. This is analogous to the concept of the singularity, a point in the universe's history when everything was incredibly close together, with extreme density and temperature. If we extrapolate the laws of physics backward in time, we arrive at a moment approximately 13.8 billion years ago when the temperature and density of the universe became infinite. However, just as we begin to grapple with this idea, it becomes apparent that the situation may not be as clear-cut as it seems. Current evidence suggests that we shouldn't necessarily apply Einstein's equations all the way back to a singularity. Observations indicate a crucial period not long after 10 to the power of -32 seconds post-Big Bang, during which the universe underwent a rapid expansion known as cosmic inflation. This period of inflation provides crucial insights into the universe's evolution on a grand scale, explaining why the universe appears so uniform and shedding light on the formation of galaxies. Yet, despite the concept of inflation, the singularity remains a challenging concept. Its extreme density and temperature bring quantum forces into play, complicating our scientific understanding. We are still investigating whether there was truly a beginning to space and time. Sir Roger Penrose has proposed a new framework suggesting that events crucial to the universe's evolution, including the formation of galaxies and stars, might have occurred before the Big Bang itself. This challenges our conventional understanding and opens new avenues of exploration. In this broader context, the ultimate fate of the universe remains a subject of speculation. As we fast forward through potential scenarios of infinity, we envision a universe dominated by photons as black holes dissipate. We confront the intriguing nature of these particles. Photons follow null geodesics, traveling along paths where time and space essentially cease to exist for them. They traverse the fabric of space-time without experiencing the passage of time. Imagine turning on a flashlight for a brief moment and then turning it off. The instant the light leaves the flashlight marks event A. The moment it reaches a specific point away from the flashlight represents event B. The space-time separation between these two events is measured using the equation 2 equals 0 ds 2 equals 0. This means that the photon emitted from the flashlight travels from event A to event B simultaneously, crossing through both points of existence in a way that cancels out any net change in the space-time interval. This peculiar behavior of photons, lacking a rest frame and not having an individual clock, aligns with a fundamental principle in physics: the constancy of the speed of light. Regardless of where you are or how you're moving, light always travels at a constant speed. If photons had a fixed reference point, it would seem as though light is not moving from their perspective. This fact challenges our understanding of the speed of light and highlights the curious nature of photons. The equations governing light, known as Maxwell's equations, possess an intriguing property. They are conformally invariant. This means that the equations remain unchanged whether you scale up or down the system, whether it's the vastness of the universe or the tiny size of quantum particles. By applying this conformal picture to the concept of the Big Bang, we can envision a scenario where the universe's initial state extends beyond the traditional notion of the Big Bang singularity. This mathematical approach allows us to describe the universe's origin in a way that extends indefinitely. Einstein's theory of relativity provides crucial insights into understanding when the universe began. According to Einstein, energy and mass are interrelated, and this relationship is further explained by Max Planck's equation connecting energy and frequency. This interconnectedness between mass and frequency emphasizes the role of mass in defining the flow of time. As we consider the distant future of the universe, we envision a scenario where the universe becomes essentially empty, populated only by photons. In this distant future, the universe's state might resemble that of a new Big Bang phase, suggesting a cyclic nature to infinite expansion. This idea, known as conformal cyclic cosmology, challenges traditional notions about the universe's beginning and end. It proposes a continuous cycle of expansion and contraction, where each cycle mirrors the previous one. This cyclic model underscores the significance of the Hubble boundary, which measures the rate of the universe's expansion as it grows and contracts in a consistent cycle driven by the interchange of dark energy. It exemplifies an immortal and interconnected reality where past, present, and future intertwine. In our everyday lives, time flows continuously, forming our experiences as a sequence of moments or snapshots. Each second unfolds, leading to the next, in an endless outpouring of events. If we were to imagine all these moments arranged, each natural event and every occurrence in the vast span of the universe, it would capture the entirety of cosmic history, from the explosive birth of the Big Bang to the formation of stars in the Milky Way, from the rise of life on Earth billions of years ago to significant events happening now. They all coalesce into our sense of the present moment. However, Einstein's theories of relativity present an intriguing twist to this seemingly straightforward concept of now. According to special relativity, an object's perception of time can differ depending on its motion. This means that people moving will experience time differently and may slice through the fabric of space-time at different points, creating their unique now slices. To illustrate this, imagine a being in a distant galaxy billions of light years away from Earth. As this being moves away from Earth, its now slice intersects space-time differently, causing its present moment to lag behind Earth's history. Conversely, if the being approaches Earth, its now slice leans toward Earth's future, offering a glimpse of events yet to come. This concept becomes even more intriguing when applied to photons, particles of light. For photons, there is no distinct past, present, or future. There now encompasses all of time simultaneously. Just as we perceive all of space as existing, so too does all of time envelop every event that has happened or will happen. This idea echoes Einstein's famous remark that the distinction between past, present, and future is merely an illusion. Persistent though it may seem, is there a universal measure of time? A master clock ticking throughout the cosmos? The answer appears to be no. Time is not absolute. It is relative, shaped by motion and perception. So where does this leave us in our quest to understand the origins and evolution of the universe? Sir Roger Penrose's cyclic model proposes a perpetual cycle of universe reboots, complicating our efforts to pinpoint the start or end of the Big Bang. In this complex cosmic landscape, we perceive the possibility of a universe continually expanding and creating new universes within itself, a timeless process of creation and renewal. When we combine quantum physics with gravity and introduce the concept of inflation, we arrive at the idea of eternal inflation, a scenario where much of space is continually expanding, punctuated by pockets where inflation halts. Within this framework, the concept of a multiverse arises, where every possible event or scenario unfolds infinitely. However, recent developments, such as the controversial claims of massive gravitational wave detections by the BICEP 2 team in 2014, have cast doubt on some of these ideas. Scientific inquiry continues to unravel the mysteries of the universe, challenging our perceptions and reshaping our understanding of the universe's vast and intricate tapestry. Nevertheless, it was later revealed that the observed waves were not primordial, but rather patterns created by light passing through the dust of our universe. This discovery raised further questions. Subsequent findings have placed strict constraints on gravitational waves, ruling out many inflationary theories. This has led to a renewed focus on the fundamental assumptions of the theory of everything. Some researchers are now revisiting the concept of the Big Bounce as an alternative to the Big Bang. In this model, the universe's smoothing and straightening result not from a high-energy random quantum beginning but from a period resembling our current state where classical physics apply. This model suggests that the universe undergoes periods of slow contraction rather than rapid expansion, eliminating the idea of a multiverse caused by random quantum fluctuations during inflation. The Big Bounce hypothesis also makes specific predictions, such as a universe devoid of large-scale gravitational waves due to the lack of energy concentration. Numerous tests are ongoing to determine the presence or absence of these waves. Another significant aspect of this hypothesis is the idea of a cyclic universe, where the universe undergoes periodic bounces. This hypothesis is currently being tested through experiments and observations. The results from these studies will not only determine the origins and fate of the universe, but also establish the relationship between gravity and quantum physics. These discoveries will shape our understanding of the universe's nature. If the multiverse hypothesis is correct, our observable universe might be just an isolated event, keeping us from grasping its fundamental creation. However, if the bounce hypothesis is accurate, our observations would represent the universe as a whole, providing insights into its fundamental laws. These forthcoming scientific results will have significant implications for our comprehension of the universe.